This is chapter 2.7 notes, linear and absolute value inequalities, page 2. So in example 3 on page 1, we solved the conjunction, which meant both of those inequalities had to hold true. Now we want a disjunction. And again, key word here is this or. So we are just looking to solutions for one or the other. So I'm going to start the same way. I'm going to add 5 to both sides. I get 2x is less than or equal to negative 2. Divide both sides by 2. I get x is less than or equal to negative 1, which is the inequality from negative infinity to negative 1 inclusive. Notice I go through the same steps on this one. I get 2x is greater than 6. X is greater than 3. That's 3 to infinity. Union. My solution can live in either of these the two pieces. Let's take a look at what this looks like on a graph. I have got solutions over here less than negative 1. Or over here, greater than 3. Notice there is no overlap. There is no way an x could fall in both of those pieces. Hence the reason for the or. Now let's take a look at absolute value inequalities. Okay, so 5. We are going to talk about what absolute value means here for a minute. We want to solve and graph the solution set. Absolute value of x is less than 3. That means whatever x is, its distance is less than 3 from the origin. So it's got to be between negative 3 and positive 3. If we wanted an interval notation, which I'm not crazy about here, that looks a little more like an ordered pair. But this picture shows what we mean when we say it is within 3 of the origin. Okay. Think about what 6 says. Absolute value of m is greater than or equal to 1. So this time I'm going to draw the picture first. If the absolute value has to be more than 1 away from the origin, more than, greater than, or equal to, I have this part right here or anything over here. So when we have an absolute value inequality set up and that absolute value is greater than or equal to some number, we have to look at the two pieces. We get m is greater than or equal to 1. We're just going to rewrite as is, or m is less than or equal to negative 1. Again, we've got that negative 1 on the other side, and the inequality changes direction, just like we're multiplying by a negative. So solve and graph the solution set. 3x plus 2 is less than or equal to 5. That means whatever 3x plus 2 it is has to live within 5 of the origin. So negative 5 is less than or equal to 3x plus 2, which is less than or equal to positive 5. I am going to solve this conjunction all together. And so I'm going to subtract 2. Working on isolating that x, and I'm going to divide everything by 3. I get negative 7/3 is less than or equal to x, which is less than or equal to 1. If I were writing that in interval notation, square brackets at each endpoint. 1, 2... Negative 7/3, we've got a closed circle. Positive 1 is our other closed circle. We want everything in between. Now, if you are unsure, if you are shading the right part, Perfectly acceptable to pick a number, 0, on that interval and plug it in. 3 times 0 is 0. 0 plus 2 is 2. The absolute value of 2 is 2, which is in fact less than or equal to 5. So pick a value, plug it in just to double check and make sure you have shaded the correct place. Here I've got 5x minus 2 has got to be further than 1 away from the origin. So 5x minus 2 can be greater than 1. 5x minus 2 could be less than negative 1. Add 2 to both sides and divide by 5. I get x is greater than 5/3. Sorry, 3/5. It is really late at night. So let me know if you see mistakes. In interval notation, I have negative infinity. Let's see, x is less than 1/5. Negative infinity to 1/5. Union 3/5 to positive infinity. On the number line, here's my 1/5. Here's my 3/5. Open circles on both. Neither of these are being included. And our arrows are going off in opposite directions.